presentation here today is the resident approach, was the end-phase half-wave. In this case, we still have to match the feed line impedance with a 9-to-1 transformer. But in this case, we're going to use a half-wave length of wire so that the antenna is resonant on the band of interest. It only operates in a single band at a time, but I'm going to show at the end here how we can convert this antenna to be able to work multi-band. A variable capacitor is used in here so that we can tune resonance, and that variable capacitor is how we're going to also get multi-band operation. The nice thing about this is no external tuner is needed. It's got zero reactance, it's resonant at the frequency you can operate on. And once again, it's the focus of this presentation. So these are the components of a in-fed half-wave. We have the half-wave of wire, half-wave length of wire. We have a very short counterpoise as a return. In the case of 20 meters, this counterpoise is only about 3 feet long. And interestingly enough, without that 3 foot of counterpoise, it just won't work. If you take it off, it just won't work. The rest of this is composed of a toroid transformer with a secondary and primary. There's end-to-one turns. I'll talk a little bit about that as well. And then a capacitor here, which is used to tune out the inductive reactance so that it is resonant at the frequency of interest. All that hooked up to a 50-ohm coax. So we're going to use a toroid with a 9-to-1 turn, end-to-1 turn between primary and secondary. The capacitor should be selected so that it allows it to resonate at the operating frequency with the inductance that you select here. And I'll go into a little more detail on that. And the capacitor is going to need to be a fairly high voltage capacitor if you're going to run more than QRP power levels. It's not as bad as what we've seen before as needing for a magnetic loop antenna, where magnetic loop antenna needs at 100 watts of need a capacitor that's rated about 4.5 kilovolts or so. In this case, you need something that's around 600 volts. So it's a little easier to maybe source a cap that'll meet that range. So time for a little math, right? Okay, we've seen that right in here, we have an LC circuit, capacitor and an inductance. It's an LC tank. So this is our equation. FO here is going to be the frequency that we want to operate in, and then you can calculate either the inductance or the capacitance based on the values that you have available. To simplify all of this, and this may not look too simple, but it's a spreadsheet, and we're going to include this on the website so you guys can play with it a bit. But I basically put together this spreadsheet, and it was really for my own use and not so much to be user-friendly, but I'll walk through it here a little bit. In this case, these are the parameters for 3 different types of Amidon toroids. This is the inductance. I'm not sure what they call it. A8L, I think it is. It's something related to the inductance per number of 100 turns or something like that. The capacitor I have is a variable that goes from 9.5 to 310 picofarads. So what I've done here is, first of all, calculated the inductance based on the different toroids. I ended up settling on this T94-2. So if I put in 18 turns for my secondary of wire on this toroid, I'm going to end up with an inductance of about 2.7 microamps. So I can take this inductance now and calculate what my frequencies would be given the min and max capacitor range I have. So I was looking for 40 to 10 meters, so this tells me I can go from roughly 5.5 to 31 megahertz. That would pretty much meet my requirement of going from 40 to 10 meters. So then here, I'm looking at different options for the primary turns. If I do 2 primary turns with 18 secondaries, I end up with a 9-to-1 transformer ratio, which tells me the impedance at the terminal should be about 4 k-ohms. So that's what I settled on. Essentially, this is where I figured I'd get the best range out of that cap. I'm using this Amidon T94-2 with 18 turns of wire as a secondary, and then 2 turns as a primary. So in terms of capacitor selection, we have to have a capacitor that selects a voltage that allows our operation at the power range we want to do, and also that has a range that will allow us to tune what we're looking for in terms of band operation. You can use a fixed capacitor. You know, you can do this calculation, come up with a fixed capacitor, and operate in one band. So it's not really necessary that you do a variable unless you're going to want to work multi-band operation. In this case, we need to handle about 650 volts for a 100 watt operation. What I'm using is a new old stock Alps variable capacitor that I got from eBay. These are, for some reason, they're shipped from Thailand. They cost $12.50. It was surplus from some of my early mag loop experiments. Clearly not suitable for more than a QRP mag loop, but for this application, it works really well. And just to go into a little bit more detail on the capacitor voltage ratings, you can kind of use this chart to gauge where you need to be for a different power range. 100 watts, you need about 686 volt rating for your capacitor. If you're going to run QRP, you can get away with a much lower voltage rating on the cap. And if you want to run, you know, kilowatt range, then you're going to need a fairly hefty cap for it. So a little on the toroid now. What I'm finding is Amadon is your friend, right? And I say that because their website here has some really great specs, and I strongly recommend you peruse that website, look over some of their specs. If you guys have ever thought about winding a toroidal inductor for a filter or for some other homebrew project you got, these guys have all the information you need to select the toroid you need, the type of toroid, how many turns of a specific gauge wire will fit on a specific size toroid. It's just got a whole bunch of really useful information that you can plug in there. And I found that a good source for these Amadon cores is a company called Ultronics. They pretty much carry all of the Amadon stock there. You can buy them fairly reasonably priced and get whatever cores you need for these projects.
Here's one thing to know. That Ultronics, there's two different companies with virtually identical names, but you're getting the right one.
Exactly. Use this website. I know that's the right link.
Yeah.
There's one that's ALtronics. Yeah, I know. Yeah, exactly.
Well, there's another one with ALL-Tronics.
That's very true. There are two different sites for that.
They were partners at one time.
Were they? Okay.
Kits and parts still all the time.
Exactly. Yeah. So, I mean, there's other sources, right? But I found that this was helpful in that, you know, they generally had what I'm looking for, and the shipping was pretty reasonable too. So, something to remember when it comes to these toroids is that for a fixed number of turns, the larger the core diameter, the greater the inductance is going to be. So keep that in mind if you start getting into trying to use a too big a toroid for a given number of turns, your inductance is going to go up, so your tuning for the capacitor is going to change. Just something to keep in mind. I'm recommending using type 2 powdered iron cores for the mesh. I found out the hard way that a type 43 is not going to work. The inductance of the primary is too high to tune. If you recall, I was looking at about a 2.7 microhenry inductance for that Amadon core that I used, the type 2. The type 43 ended up with 500 microhenries, which just completely unable to tune it with the range of cap on it. So once again, I selected a 9-to-1 ratio on a T94-2 core. I'm using 18 turns of number 22 magnet wire, insulated magnet wire for the secondary, and 2 turns for the primary. The inductance ends up being about 2.7 microamps. This is just a quick view of the parts as I started putting it together. I just mounted it all in this little plastic project box. I've got the cap, the toroid, and a connector. It's not hard to wire these things up once you have the toroid wound. You just basically wire the primary across the capacitor terminals and also a set of banana jacks. And you're good to go. This is the finished unit. And I'm actually testing it here. This quote by Steve Yates is really a key here. To get maximum success off of one of these antennas, they recommend he recommends basically putting a resistor across the terminals and finding the resonant point on the capacitor in that way. So if you look here, essentially I've got a 4 k ohm resistor, which that spreadsheet gave me the value I needed for that.
Right.